All right. Well, I'm very happy that Marcus was able to come to Edmonton, even though we're in the middle of our fourth COVID wave. I first met Marcus when we were working together at Borealis, and many of our interactions were, Marcus, I don't understand this. Can you explain it to me? And one of the reasons I'm so excited about having him here is I think he's a really great communicator. And he's been doing some really interesting stuff with normalizing flows, which I still have trouble getting my head around, but I think they hold a lot of promise. So if you're interested in Marcus's full CV and bio, you can find that on his website. He told me it's up to date. I will point out, though, that he's an assistant professor at York. He's working at Borealis and with Samsung, I believe. Yes, Samsung AI Center. So he is also interested in real world problems, not just academic stuff. So I encourage you, if you have time later this afternoon, if he has time on the schedule, maybe find a time to chat with him, because he's just a great person to talk to, both professionally and personally. So with that, I will hand it over to Marcus.
Well, thank you, Matt, for that very generous introduction. I hope I can live up to the expectations you've set for me. And I will say, yeah, I'm very happy to take questions along the way. I'm happy to chat afterwards with anyone. I know there's, I think, one or two people that have signed up to chat with me afterwards. But if you're, if this afternoon doesn't work for you and you want to chat or ask me questions, feel free to drop me an email or find me. Otherwise, I'm happy to set up a time. Okay, so let me get started. And before I dive into kind of the main bulk of the talk, I just want to talk a little bit about what my high level kind of research vision or interests are. My background is kind of computer vision, machine learning, a bit of statistics. But the thing that kind of drives me is understanding models of the world and in computer vision in particular. And I find modeling kind of an interesting area because, I don't know, I like to learn things about the world. And I like to see how we can make the models and the algorithms and the methods that we design that are trying to understand the world, learn and know about those things as well. So, you know, I think computer vision is a great domain where this is the case, where, you know, our goal in computer vision is to take images in the world and try to estimate properties. So we have our picture from our camera. We want to know something about what's there, what are the objects, what's the shape of the world, things like that. But we have this really rich source of knowledge that exists out there. We don't as well know how to do that, but we have a long history of going the other direction. We have information, you know, we've known about perspective for hundreds of years. We've understand kind of the geometry of cameras, and, you know, we understand basics of photometrics. And so there's all this extra domain knowledge that exists out there that is should be valuable for us in terms of you know, computer vision and AI researchers trying to solve these kind of inverse problems, if you want to think of it in those terms. And I find in real world applications, this is actually a really critical thing because, you know, modern machine learning has kind of, you know, for the last 10 years or so, the field has taken this perspective that says, you know, domain knowledge is less important, just give me a lot of data. And we've done incredible things with that perspective in the last 10 years. But, you know, a lot of cases in the real world, we just don't have that much data, right? Or we can't afford to collect that much data, or maybe real data doesn't exist. Maybe ground truth labels for your problem doesn't exist. And so we need to also understand what are other sources of knowledge that we can bring in, how can we bring them to bear? And I personally find, you know, these sorts of domain knowledge and domain expertise a really fruitful and interesting source of knowledge. So just a couple of examples of projects. This was a robotics project I worked on a couple of years ago, actually as part of a postdoc with Raquel Ertazan, looking at localizing vehicles and maps. You know, this is a kidnapped robot problem, if you're familiar with that terminology from robotics. All we did here was we took topographical maps from OpenStreetMaps and we took visual odometry, and we were able to kind of localize a car driving in a street grid or street network down to an accuracy of about 3 meters, right? So this was, you know, this domain knowledge in this case was kind of pulling in this road network information that we have just sitting there. Another big one that I spent a lot of time in over the last couple of years is electron cryomicroscopy. This is a technique that you can use to determine the three-dimensional structure of biological molecules like proteins and viruses. And so you take this sample of your protein, you freeze it into a really thin film, and then image it in electron microscope, and you get these absolutely horrendous images out. And the goal of the problem is to try to actually recover three-dimensional structure from this. This has been a really fun, kind of rewarding project. In fact, the very first structure of the SARS-CoV-2 spike protein was determined with Cryo using software that I helped write about 2 months after it was originally sequenced. But that's another one where we really have to pull in domain knowledge. We have to understand, you know, we don't have ground truth because fundamentally we're looking at images of three-dimensional objects that we don't know. And we have to exploit the knowledge that we have of the optics of the microscope and the physics of the image formation model and things like that, to be able to solve the problem. Lots of other stuff I've worked in off and on, MCMC methods. I worked on a project called STAN, which if you've done some applied Bayesian statistical analysis, you might be familiar with. Dynamic texture synthesis a couple of years ago was a fun project generating, automatically generating images like this. Worked in ballistic forensics, medical imaging, some recent work on imagery coloring with GANs. And then of course the title of the talk, Normalizing Flows. And this has been kind of my main focus over the last, let's say, 3 years. So what are normalizing flows? If you've never heard of them before, or if it's just you've never really been quite clear on what they are, they're they're in a generative model built on invertible transformations. Okay, so one way to think about it is that they're just a really complicated probability distribution. Okay, it's a really flexible, really expressive class of probability distributions that we can construct that have a certain set of desirable properties, in my view. They're generally efficient to sample from. So if we have this distribution over, let's say, our data X here, we can randomly sample, we can randomly generate samples from this distribution exactly, relatively efficiently. We can also evaluate the normalized probability density of these points efficiently. They are fairly highly expressive and relatively straightforward to train. And so these are all kind of, I think, these are in my view, the desiderata of a good generative model. And normalizing flows kind of check all of these boxes. You might not have heard of them quite as much. They have not had quite as much success yet. And I think that's in part because they haven't had as much research attention, and that's been changing over the last couple of years as well. If you want to go back in history a little bit, I can give you a really brief tour of the history of it. So I kind of start the timeline here around 2010 with work by Tabak at the Courant Institute. The ideas that underpin normalizing flows actually goes back a lot longer than that. There's papers on something called Gaussianization, which has been around in the statistics literature for a long time. It's closely related to things like nonlinear ICA, copulas, and those sorts of things, if you're familiar with any of those terms. But 2010 was when I believe, to the best of my knowledge, the term normalizing flow was coined in a series of papers over 3 years here. There was in 2013, then there was a paper by Ryan Adams from Harvard looking at density estimation that never really went anywhere. I think this was an archive-only paper. It wasn't published at any conference or workshop, but it was actually kind of the first one that really started, you know, certainly in the machine learning community and around, really pushing these as like generic density estimators. 2014, we had a paper called NICE, and then the one that kind of, I think, started to grow the momentum would have been this paper by Danilo Rezende and others in 2015, introducing normalizing flows for variational inference. And so in this context, flows weren't even being introduced as an actual generative model themselves. They were just trying to be used as a way to make VAEs more effective. And then 2016 was kind of the big year where Laurent Din, as part of his PhD work at Mila, looked at using these directly for normalizing flows directly for density estimation, and introduced the real MVP architecture. And probably 80 to 90% of normalizing flow architectures these days are kind of very closely based on the real MVP architecture, with kind of some small changes here and there. And we'll talk about that. It was notable because it was able to generate some fairly nice looking images while still having kind of all of those nice checkbox that we mentioned earlier in terms of a generative model. And then there was, not a lot of work on it, but a few papers here and there. A few people were kind of playing around with it. Laurent continued working on it as well. And then in 2018, the GLOW paper came out. And this was the paper that really kind of caught my attention. And the reason was, normalizing flows were there. People were like, yeah, but the image quality is not as good as GANs. They don't really look that great. It'd be nice if they worked, but they didn't. And the GLOW paper, had this level of results, which, compared to now, if you compare this against the best state-of-the-art GANs that exist out there, there are better image generation results, but these were, stunningly good for a model that kind of ticked all of those other boxes for a generative model. It allowed you to do some nice interpolation. So this is Darawal, who's one of the co-authors of the GLOW paper, interpolating in the latent space that comes out of a normalizing flow. To other faces. I don't know why that animation didn't. Oh, there we go. Interpolating to other faces. It's kind of a very nice result that came out of it, and something that is, was challenging to do with some of the other generative models at the time. So that's kind of the backstory. But what are normalizing flows? I'm going to give you a couple slide intro of what normalizing flows are, and then I'm going to talk about two different projects that I've worked on using normalizing flows or kind of extending them. So normalizing flows is really just, I'm the worst salesperson ever, because I'm totally going to undersell this. They're nothing more than the multivariate change of variables formula from your basic probability course. Okay, so this is the change of variables formula. There's many different forms of it that you might have seen, but basically what you have is some invertible transformation, some function f that has to be invertible and differentiable. And we're transforming some random variable x into some other random variable z. Okay, and we're trying to relate the density of those two random variables x and z. And this is the relationship between those variables. Okay, so we have the density of z, we have our invertible transformation, we have this other term here, which is the volume correction term, or it goes under a bunch of different names. And this d here is just the Jacobian of that transformation function f. Okay, so this is just review of basic probability in essence. Okay, conceptually, what we can think of is we have this distribution over x, which is maybe very, very complicated. In this case, it's bimodal. Maybe it's more complex than that. And we can run it through some form of invertible nonlinear transformation. So in this case, I've chosen to run it through the cube root function. And it turns out that if you run this bimodal distribution, if you run the random variable associated with this bimodal density function through a cube root, what you get out is a nice, simple unimodal thing that looks like a Gaussian. Okay, and that's the change of variables, right? So we can take this complex distribution, transform it into something else. There's some fundamental results in probability and statistical theory that tells you you can basically transform almost any distribution into almost any other distribution under some assumptions, under some conditions. And that's what the idea here is if we have a model like this, what can we do? Right? So if we have a very complex function f that transforms some complex distribution into a simple one, we can do things like density evaluation. Okay, so if you imagine that we have some complex distribution, let's say a distribution of images, the way we do density evaluation is we just transform those images through this invertible function f that should transform that image into a sample of, let's say, Gaussian noise or whatever we choose that base distribution to be. And now we can evaluate the density of it, and we can take the determinant of the Jacobian, and now we have the density in our complex space. Okay, and sampling is also relatively simple. This function f has to be invertible, and so we can draw a sample from our base distribution here, from the noise distribution on the bottom. We can run it through the inverse, and now we've generated a sample that's consistent with this density function as well. Okay, and in fact, this change of variables in probability courses, when it's presented, it's often shown as a way to, you often use it to construct random generation algorithms for new, more complex probability distributions exactly in this way. Okay, and so learning a generative model like a normalizing flow is basically saying, given some samples from our data distribution, we want to find an invertible differentiable function f, such that this distribution over x that we get roughly approximates the data distribution based on our samples, right? And so we're just trying to learn this mapping of our complex distribution into this nice, simple distribution. Okay, and training can proceed via simple maximum likelihood. Yes, Matt, go ahead.
So I'd like that example with the trees. So I could see how if you had not a whole lot of data, then you could use this to generate more trees.
Yep.
How do you know that the trees that you generate are good enough, are close enough to be useful?
I mean, that's always kind of the crux of the problem with the generative model, and it connects back to the same sort of generalization type questions that we might ask about any data-driven machine learning model, right? It is generalization in the context of a probability distribution. There's a longer conversation that I'd be happy to have at some point about how we train these distribution models and what we can expect from the practicality of the samples. There's certain good reasons to choose training by a maximum likelihood. If you care about sample quality, you might choose to train with something else. But yeah, you just kind of have to test and validate to make sure that your model is actually learning the distribution that you want. And so one of the nice things is you can actually have a held out test set or validation set that you can evaluate your model on, unlike, for instance, with GANs, where you can't really evaluate how well your model or how likely your model was to generate a particular image. You can do that with this. And so you can evaluate the log density of a bunch of held out tree images, for instance, and see whether or not it also assigns them good probability.
Okay, that helps, because otherwise it just seems like magic where you can just make up new data.
Yeah, absolutely.
Okay, thank you.
Yep. Okay, so we can do training by maximum likelihood. This is what it kind of looks like at the end of the day. You get this nice sort of decomposition between the probability of your data points transformed in the latent space. That's the first term there, and then you have this other term, which is the volume correction term, the log determinant of the Jacobian, right? And so we have some parameters that we're going to optimize, and we can do this using standard gradient descent or stochastic gradient descent, just like we're used to doing in lots of other contexts with modern machine learning. Okay, so what is a flow, though? What are these functions, right? So we refer to a flow as a parametric function that has the various properties that we need in order to be able to apply that change of variables formula. Okay, so it's invertible, needs to be differentiable. From a practical perspective, we want it to have an efficiently computable inverse and Jacobian determinant. Okay, you can have functions that are theoretically invertible everywhere, but maybe that inverse is very, very hard to compute. Or maybe the Jacobian is very dense and its determinant doesn't have a nice simple form. And so hitting all three of these marks is kind of one of the major research questions in normalizing flows. Okay, they go under a bunch of different names: flow layers, bijections, etc. And as I said, designing and understanding what they mean for the distributions that you're estimating is kind of the core research problem here in normalizing flows. One of the ways, though, that we build up complex flows, and in fact, the origin of the term normalizing flows, is that we can compose invertible transformations. Okay, so if we start off with some very complex distribution here, maybe we have a very simple invertible differentiable transformation. Okay, and we apply that transformation, let's call that F1. And what we've done is we take this complex distribution and we make it a little less complex. Okay, still lots of bumps, still multimodal, but a little less complex. And then maybe we apply another transformation, F2 here, and now we get an even smoother distribution, and F3. Oops, there we go. F3 and F4, until we have transformed gradually through this series of small incremental deformations or small incremental transformations of our distribution, this very complex distribution on the left, into a nice simple Gaussian distribution on the right. And we can just look at the overall transformation as a composition of all of these things, right? And this relies on the fact that the composition of invertible differentiable functions are themselves invertible differentiable functions. And obviously, if we can compute the inverse of all of these functions efficiently, then we can compute the inverse of the composition efficiently, and the determinants and all of those things kind of compose very, very nicely. Okay, so if we have a way of putting together these small building blocks, we can put them together just like layers in a neural network to build more and more complex functions by adding more and more transformations. And then the inverse just follows by going the other direction in the opposite order, okay? And this is, again, this is where the term normalizing flows comes from, because you can kind of think of flowing your complex distribution into the form of a normal distribution, right? Transforming it into this standard-based distribution. But of course, what are these individual flows? You know, a simple one, a really easy one to understand is a linear transformation. A linear transformation can be a flow so long as the matrix is invertible, right? So long as A is not singular. It's inverse and determinant. Determinant of the Jacobian is very easy to write out. Okay, just solving a linear system, and the determinant of the Jacobian is just the matrix A. So the determinant of the Jacobian is just the determinant of the matrix A. Linear flows actually turns out are very important, but have a fundamental flaw. One is that the determinant or inverse can be very expensive if there's not special structure to it. But more important than that is that they are fundamentally inexpressive, at least in the regime of trying to compose transformations, because the composition of linear functions is, of course, closed, right? So we take two linear functions, we compose them, we're going to get another linear function out. So we can't stack linear flows one on top of the other and expect to get a more complex transformation out of it. And that's where something called coupling flows come in. Now, this was what was introduced in the NICE and Real MVP papers by Laurent Din. And this is, you know, probably the basis of about 80 to 90% of the papers out there that use or apply normalizing flows in one context or another, okay? Maybe more. So it's a general approach to constructing nonlinear flows, nonlinear invertible differentiable transformations. The idea is a little strange at first glance, but relatively simple to explain. You take your parameters, your input to this transformation X, you split them into two disjoint subsets, XA and XB. And then what we're going to do is we're not going to touch A, and we're going to transform B, but the way we transform XB is going to depend in some very complex way on the parameters of XA. And if this looks, you know, if this notation is not working for you, that's fair. I'm going to explain this in pictures, okay? We'll come back to the equation a little bit later. And I know if you've never seen this before, this seems a little strange. Bear with me, I'll explain why we do it this way at the end, okay? Or why this is a good idea at the end, at least. So we take our input X here, we're going to split it into two halves. So we have XA and XB at the top. XA, we're not going to touch. It's not going to get changed at all. We're just going to go stick it over here on the side, and it's going to kind of, you know, just sit there, okay? But at the same time, we're also going to run it through what we'll call a coupling network, which is this transformation, this function theta. All right, so it takes as input XA, and it spits out a bunch of parameters. And those parameters are going to be what controls the coupling transformation, okay? And so this coupling transformation, it needs to be another invertible, it needs to basically be another flow, okay? But it's a flow whose parameters are going to be determined by XA, and it only is going to transform the subset of parameters XB, okay? So we transform our parameters XB, okay? And now we get out this changed set of parameters. We're just going to concatenate these two things back together. And now we have our coupling transformation. Okay. That's the forward pass of this. This is invertible. Okay. And the key to this being invertible is the fact that we haven't changed XA at all. Okay. So that's completely undone. Those parameters are already given, and we can run those exact same parameters, those exact same values of XA back through the coupling network in the opposite direction. Okay, to get the right parameters to feed into that coupling transformation, which by definition we've said has to be invertible as well. Okay, so conceptually we can say we start off here with Z, which is our transformed data point. We're also going to split it, so we have ZA and ZB, but ZA, of course, is just the original parameters XA. Okay, because we haven't modified those, and we can run them through the coupling network. We're going to get back exactly the same set of parameters that were used in the forward transformation, and we can use them to compute the inverse with the inverse of the coupling transform. Okay. And now we run through F hat inverse here, applied to ZB, and we can concatenate them back together. And now we've fully inverted this coupling transformation. Okay. Is this, and that's the form of the inverse. Is this, hopefully this is clear. Again, please feel free to interrupt me if not. However, of course, I have not actually told you why this may seem indeed like a very strange thing to do. And it has to do with that practical property that I indicated for a flow. Okay, so this is invertible and it's differentiable so long as f hat is invertible and differentiable. Okay, but the key piece of this is that this coupling transformation, if you look at the Jacobian of the coupling transform, it has a specific structure. Okay, let's see here. There we go. The structure of the Jacobian looks something like this. Okay, so in the top left block, that's a derivative of ZA with respect to XA. That's just the identity, right? Because we don't touch XA at all. And the top right block in this Jacobian is 0 because ZA doesn't depend at all on XB. Okay, because that's just, we just take XA as is, right? So it's the derivative of that of the first row of the transformation on top there with respect to the second set of parameters. Okay. The bottom part of that Jacobian, let me see if I can, I will do this way. So this part here is just the derivative of that with respect to X, okay? And now this bottom row, let's just focus on this term here. So this is just the Jacobian of our coupling transform. Okay, so we're going to assume this coupling transform, by the way, could be very simple. This could just be a diagonal linear transformation, right? So it's just a diagonal matrix and the parameters are just the entries on that diagonal. Okay, so that means that the Jacobian of that is going to be a diagonal matrix. That means that the determinant is really cheap and easy to compute. Its invertibility is easy to ensure so long as those diagonal entries, those parameters that come out of theta, are non-zero. Okay, and the reason why all of this is important and the structure of the Jacobian is critical is because that means the determinant of the entire transformation, right, is the determinant just of that coupling transform. Okay, and this is relying on the fact that this is a block triangular matrix, and the determinant of a block triangular matrix is just the product of the determinant of the diagonal blocks. Okay, so the determinant of the identity is just 1, and then we're just left with the determinant of f hat. And notice that, let's see here, that this term here, this is the term that depends on theta. It depends on that network that transforms XA into a set of parameters for a coupling transform. That doesn't show up in the inverse. It doesn't show up in the determinant. We don't care what it is. And practically what that means is we can make that theta be as complicated and convoluted as we want. It can be absolutely any function so long as it spits out a valid set of parameters for a coupling transform. Okay. Is that any questions on that? Sorry, Carlos is asking, the set note. I'm sorry, Carlos, I'm not quite sure I understand what you're asking. You mean the sets of the values and the inputs and outputs, like the domain and range? Yeah, so you prefix the way that you subdivide you subdivide your dimensions. Okay, and in fact, there's a key subtle point here which you might be picking up on, which is if you always split it the same way every time, your coupling flow will never change the first half of your parameters. And so typically you might randomly assign points, dimensions to XA and to XB. And the only thing that you need to do is just make sure it's a disjoint partition. Okay. All right. Any other questions? So these are coupling flows. Okay. So the choice of coupling transform in a coupling flow is there's lots of different options. You can just have really simple ones where it's just a scalar offset. That's an additive transform. That was in that original NICE paper. Real MVP added this notion of affine transformation. So you have that diagonal linear operator as well as an offset. People have explored lots of other variations of more complex coupling transformations. People have used special types of multi-layer perceptrons, the CDFs of complex distributions, splines, things like that. Anything that you can make invertible. Typically, all those techniques are applying them element-wise to each dimension independently. So it's any 1D invertible differentiable transformation, you can do that element-wise. I should just, for completeness sake, I should add, there is other work other than coupling transformations, other types of flows other than coupling transformations, which are really, really interesting and exciting out there. They just haven't had quite as much traction in practice yet, I would argue. Neural ODEs, which many of you might have seen. It was a paper at NeurIPS a couple of years ago. You can use neural ODEs as your transformation. So a solution of an initial value problem is effectively your transformation, which is actually a really elegant model, has some really, really nice connections to optimal transport theory. Residual flows, it turns out you can, with small tweaks, you can take a ResNet architecture and you can make it invertible and use it for normalizing flow. And then there's a really nice paper at ICML last year, which kind of pulls together normalizing flows and VAEs in a different and really interesting way. It's from Max Welling's group called SurVAE flows, or which introduces surjective flows. So now your transformations don't strictly have to be invertible. And then you have to do some sort of variational approximations, but they have some nice properties and are, at least to me, a really interesting kind of class of methods that are out there. Okay, so that's my like really probably too long, but relatively fast intro to normalizing flows. Any quick questions on that before I dive into the next thing, which is going to be one of the applications that of normalizing flows that I've explored?
I have a question. So,
sure.
Which mechanism in normalizing flow guarantee that you change the input domain to, or you approximate the input domain to a Gaussian distribution, something like that?
Yeah, so I mean, there's no guarantees. Just like in kind of almost everything that we do in machine learning, we have very little in the way of absolute guarantees. There are, from a theory perspective, there are universal approximation theorems that apply to normalizing flows and kind of the infinite capacity, infinite data limits. But in essence, one way to think about normalizing flows is that the invertible transformations give us a way to construct a very expressive parametric family of distributions. And we can try to estimate the parameters of those distributions by trying to maximize the likelihood of our data, right? And so we will fit that data, we will approximate that distribution as well as a maximum likelihood estimate of those parameters will allow us.
Oh, so there might be some cases that the final distribution they encode is not follow the normal distribution. There may be others. So
yeah, so in fact, if you do not approximate the data distribution well, what you will find is that the distribution in the latent space will not look like a Gaussian distribution.
Oh.
You'll see structure and patterns in that you would not expect to see from a Gaussian distribution. And in fact, an interesting direction that I've considered is there's a whole literature in statistics on Gaussianity testing, kind of testing whether or not a set of samples follow a Gaussian distribution. Those would be excellent heuristics to try to apply to fitting normalizing flows, but just never gotten around to doing it.
Okay, thank you.
Okay, so one question popped up here in the chat. Yes, so is asking how normalizing flows compare to things like bidirectional GANs. Yeah, so things like bidirectional GANs, you're typically trying to approximate the inverse of the generator in a GAN. And one way to think about that, and in fact, somebody's already done this, which is if you took a generator and you replaced it with an invertible transformation, okay, then you wouldn't need to do bidirectional GANs because you could just directly invert that function. And if you do that, that's actually exactly a normalizing flow. And what I just talked about shows that if you did that, you could then actually compute the likelihood of any image under your generator, under your GAN, right? And in fact, there's a paper called FlowGAN that was at, I think, UAI a couple of years ago, where they did exactly that. They took a normalizing flow architecture and they plugged it in as the generator of a GAN. They trained it, using an adversarial training regime. One of the nice things they were able to do there was that you could then stabilize the GAN training, the kind of adversarial GAN training, by adding a little bit of maximum likelihood into your objective whenever you're updating the parameters of the generator, right? Because it is invertible. Great question, though. Okay, so let me talk about two recent, relatively recent pieces of work. One is noise flows. So this was joint work with an intern actually at Borealis, Abdulrahman and Michael Brown. Michael's a low-level kind of image processing camera guy. And so they're very interested in questions around camera noise. And so for those of you working in computer vision, of course, we work with images all the time, but of course our images are never pure readings or pure measurements of light. They're often corrupted by noise, okay? And that noise has some very specific structure. So we can see some example of this noise. And if we take a look at it, I'm going to kind of blow this up here. Here we are. There we go. We can get a clean version of this image. We can subtract it off. And this is the difference between a clean version of the image. Don't ask me how we got it. And one of those noisy samples of the image that we were looking at. And if we plot a histogram of this, what we'll see is that this looks kind of Gaussian-like, but it's definitely not Gaussian, right? So this is the best fitting Gaussian that we can find for these noise samples. Okay, so it's definitely not Gaussian. And worse than that, if we take this and we amplify, we kind of increase the contrast a little bit of the noise, what we're going to find is there's structure in this noise. Okay. And in fact, if I overlay this noise a little bit on the original image, what you're going to see is that the structure that we see in the noise actually lines up with structure in the image. Okay, so the noise is actually correlated and dependent upon the underlying clean signal intensity. Okay, this actually shouldn't be terribly surprising to people if you're familiar with physics, because physics tells us that if you're counting photons that are arriving in a region, the count of photons that we have follows a Poisson distribution. That Poisson distribution has this property that says the variance of the distribution is equal to the mean of the distribution. Okay, and in fact, when we look at the variance of noise in images as a function of intensity of the clean image, we see this very, very nice linear structure. Okay, that's what's being plotted here. The x-axis is intensity, the y-axis is variance of the noise. And so we can fit a really nice linear function to it, and it approximates it pretty well, except for kind of the two endpoints there. And we'll talk about that in a minute. But this is what's sometimes called this is a signal dependent noise model, or sometimes called a heteroscedastic Gaussian noise model. But the problem is it doesn't capture everything perfectly. Okay, so what else is there? I'm not a low-level camera person, so please don't ask me any questions about any of this. I just know that it exists. But there's all sorts of other things. So for instance, if you took a picture, dark signal non-uniformity, if you took a picture of a completely dark room with a camera, you will not get a completely black image. There can be defective pixels that will register, that will always be saturated or always be dark. There's fixed pattern noise due to manufacturing defects. There's thermal noise that fluctuates depending on the temperature of the sensor. There's noise due to amplification or gain of the analog signal before it gets converted to a digital signal. There's clipping at either end. There's over or under exposure, all sorts of things like this. So there's all these other phenomena. And basically the reason this is all there, the reason why it doesn't follow this nice, clean Poisson-like noise model is that we're not actually directly counting photons. We count photons through this sensor. And the sensor has all these different things, right? So we have electronic noise that feeds into it. We have noise from the amplifier that I was mentioning. We have readout noise whenever we actually try to pull the analog signal off the sensor. We introduce noise and errors whenever we quantize and convert to a digital signal from an analog measurement, and all sorts of things. And all of these pieces are actually somewhat well understood, but they're all completely different for every sensor, every different sensor you look at. We don't really know what they are for most sensors in practice, and they're really, really difficult to model analytically. Okay, and so the idea behind this project is let's learn a compact, convenient model of camera noise, where we exploit the domain knowledge that we have about what's happening with noise in the camera. Let's exploit the information, what we know about this noise process. But let's use normalizing flows as this kind of, sledgehammer black box set of transformations that will hopefully capture all of these other phenomena that we might have in here. Okay, so what does that actually look like in practice? Well, we start off with Gaussian noise, and the very first thing we're going to do is we're going to take our clean image, we're going to take a linear transformation of the clean intensity, and we're going to use that to get a scaling factor that we're going to multiply the noise value at each corresponding pixel by. And this is complete, if I stopped this right here and I said noise comes out the other side, this is exactly the heteroscedastic Gaussian noise model. okay? But it's also, you can also view it as an invertible transformation that will be part of normalizing flow, because all you're doing is just a diagonal linear transformation, which in this case is conditioned on the underlying clean image intensity, okay? But if you remember, that photon noise starts at the left, and then there's all sorts of electronic noise and all sorts of other things that come in and start to impact and manipulate the noise and the signal that we're reading off the sensor. And we don't really know how to model those things. So the next thing we're going to do is we're going to plug in some affine coupling layers. Okay, we're going to plug in some just black box nonlinear flow transformations here, because we're basically saying we don't know what happens here, or at least we know what happens here, we just don't know how to model it well. Okay. The next thing that happens in that pipeline, if you remember from the slide before, is we have some, there we go, we have some amplification, right? So we have a gain. This is, the ISO setting. It might also be somewhat dependent on the camera. Different cameras will have different amounts of noise in their amplifiers due to different configurations. And then that's a nice simple invertible transformation, because it's just literally multiplying the whole thing by a scalar factor that's dependent on the noise and camera. And then we have another set of black box flow transformations that further manipulate it, kind of capturing the things that we don't know. And then we split out the actual noise itself. And this entire model we call the noise flow model, okay? And we're pulling together all these different pieces, the kind of black box pieces from the normalizing flows literature, as well as these kind of specially designed flows that are motivated based off of what we know about the world and what we know about the noise process in this sensor. Now, to train this, what we need is we need a bunch of images, a bunch of noisy images and corresponding clean images. And thankfully, Michael and Abdul had collected such a data set a couple of years before we were doing this project in terms of SIDD, the smartphone image denoising data set. If you think it's easy to collect clean images for things like this, I would encourage you to go read this paper. It is not. It turns out you have to take into account things like flicker of light. You have to take into account the fact that cameras often have optical stabilization mechanisms that cause the image to jitter by a pixel or two here or there that you basically can't turn off. All sorts of things like that. It was a very large amount of work to collect and capture this data. Okay, but we took our noise flow model, we trained it using maximum likelihood. And we can kind of compare it against a bunch of other models. So these are just sampled images, some example images shown here. We have the clean corresponding image patch on the right. We have a real sample of noise in the next column moving left. We have our noise flow sample, and we have the heteroscedastic model, and then we have the simple Gaussian model. Okay. And what we find kind of both qualitatively and quantitatively is we're definitely doing a much better job approximating the noise and the noise distribution using the noise flow model that we've constructed. Okay, now going back a little bit to Matt's question, the interesting thing about this is that we can actually use this to generate training data, for instance, for a denoiser. Okay, so we can take a bunch of clean images, and every time we get a clean image, we can give it a new sample of noise, and we can train a denoiser with all of these pairs. Okay, and it turns out that if we train if we look at the first few rows of this table, we see, okay, what happens if we train with Gaussian noise? Well, that works okay, but not very good, which is interesting for people that have looked at denoising in the past. People have trained with synthetic Gaussian noise for 40 years of denoising research, and it turns out it's not a good approximation. We have the camera noise level function, which is basically just another term for the heteroscedastic Gaussian noise model, which works a bit better than simple isotropic Gaussian noise. And then we have our noise flow model, which is about 3.5 decibels improvement in terms of the quality. But the really interesting point here is that last line on the table is those clean noisy pairs that we use to train the noise flow model. We can also just use those directly to train our denoiser. And it turns out that we actually train a better denoiser by first training a noise model and then using that noise model to synthesize data, then training directly on those clean noisy images by a full 1.5 decibels, which is a pretty large margin in terms of denoising performance. And the explanation for this is, one is we're incorporating more domain knowledge into our noise model, okay? And we're also giving the network many more samples of noise for it to be able to understand and differentiate between what is clean signal and what is noise in our images, okay? Okay, so quick recap: noise flow, realistic practical model of camera noise in real images. We're using kind of domain knowledge about how the noise process actually physically works in a camera to help capture these key properties, but mixing that in with normalizing flows to kind of capture everything else that happens that we don't know how to model. Okay, lots of other things that we have to look at going forward: realistic camera noise and other applications, as well as other places where camera noise, other types of camera noise that maybe we can construct specialized flows to capture. Russ, what are the error bars? Is this significant? That is an excellent question to which I should have an answer, but I don't off the top of my head. This is over a pretty large data set. So my guess is the error bars are reasonably tight in terms of, at least to the extent that there's uncertainty driven by data set size, but I don't have the answers off the top of my head. Okay, any other questions on this? We are really coming up on time, so the next section is going to be pretty quick. I'll go through it relatively fast just to give a flavor of it, and then we can talk about more details later. But I'm happy to take a question on noise flow now if anybody has something burning. No? Okay. The last one I'll talk about, this was a NURBS paper last year, wavelet flow. And it was motivated by this idea of looking at scale structure in generative models. And normalizing flow architectures typically, at least traditionally, have lacked a notion of signal scale. And so if you train a normalizing flow on a set of images at 128 by 128, and then you downsample all those images to 64 by 64, and you train another normalizing flow on those lower resolution images, it's entirely impossible that those two models are going to be completely inconsistent with each other. One might work very well, one might work very poorly. They're not at all connected, and we can't easily extract a low res model out of our 128 trained model or vice versa. Okay. It also means that training for high resolution imagery is very expensive. That GLOW paper that I mentioned, I think they used basically roughly a GPU year or two worth of training in order to train the model. And so GANs and VAEs and other generative models have exploited signal scale for kind of faster and high resolution training, but no one has really looked at how should we do it with normalizing flows, and that was what kind of motivated this project. And so how do we capture scale structure? Those of you who have gone through some computer vision courses might know of image pyramids, things like Gaussian and Laplacian pyramids, but one of the challenges with them is that they're overcomplete. Okay, a Gaussian pyramid or a Laplacian pyramid has more values, more dimensions than it does than the original image has pixels. And that means that maintaining invertibility of the transformation to a Laplacian pyramid and back is difficult. And so the solution that we came up with was to look at exploring wavelets. So a wavelet transformation, if you've not seen it before, takes an image and it basically splits it into two pieces. Okay. One piece is a low pass filtered version of the image that's lower resolution, so it's half the size. And the other is basically all the information that you lose by going down to half the resolution. Okay, so you low pass filter your image, and then you keep around, you have these detail coefficients, and wavelets tell you how to compute these that tell you exactly what you lost when you went down to low resolution. Okay, so this is now an n/2 by n/2 image, and then we have n/2 squared by 3. And if you work out the math, you'll see that the dimensionality all adds up, so that if you take all the detail coefficients and all the pixels of the low res image, you have back your original n² number of dimensions. Okay. And so we can iterate this. Okay. And we can apply the wavelet transform again on the n/2 sized image, get another even lower resolution image, it's n/4, and another set of detail coefficients. There we go. And we can just continue going on down and down and down until basically you have a 1x1 image, a single pixel image if you want. Okay, but you could stop anywhere along the way. Okay, but this is the wavelet transform. And we can invert this process. We start with whatever our lowest resolution, wherever we stopped the wavelet transform, and we just recombine that low res image with its corresponding detail coefficients to get back a slightly higher resolution image, which can then be combined with the detail coefficients of the next level up through the inverse wavelet transform again, and getting back originally to the high resolution image. Okay, so this is a transformation that kind of decomposes our original high resolution image into detail coefficients at a set of scales and some ultimately low resolution image. Okay, and it has a number of nice properties. Formally, we can write it like this, but basically the key things are it preserves dimensionality. It's actually a linear transformation. It's invertible, and if we set it up right, it turns out that it's actually an orthonormal transformation, which means that the determinant is 1. And if you recall, if we're using the change of variables, that determinant of the transformation is actually an important quantity that we need to know. Okay, and we can at any point along the way, we can pull out a lower resolution image if we want out of this wavelet transform. So the wavelet, a couple questions in the chat here. Yes, the wavelet transform is lossless in essence. It's perfectly invertible. Let me continue through this, and I'm happy to take any more questions. I should say we definitely don't have time for a full review of wavelets. There's a long history of wavelets in signal processing that I could not even hope to cover in the time that we have, but I'm happy to answer questions at the end here. And so the nice part of this is that the wavelet transform kind of fits very naturally as a normalizing flow, right? Because basically it's a linear transform, just like the linear transforms we talked about earlier. It has a special structure, which means that its inverse is easy to compute, and it means that we know what its determinant is if we set it up right to start, okay? And so how are we going to use that to construct a normalizing flow of high resolution images? Well, first off, we're just going to apply the change of variables. And what we can see is we can write the probability of some high resolution image IS here as under this wavelet transform as the probability of my lowest resolution image, and then the probability of all the detail coefficients, right? So this is just straight applying that wavelet transform as the change of variables in the change of variables formula, okay? We're going to take another short step here. We're going to use the product rule of probability, okay? And we can factorize this distribution exactly as the probability of the low res image times the probability of the low res detail coefficients given the low res image times the probability of the next set of detail coefficients given the previous detail coefficients and previous low res image, and so forth. Okay, so we can factorize that using the product rule of probability. And now we do one last step. We apply the inverse wavelet transform at each scale along the way, and we get this nice factored form, which is the probability of the low resolution image, I0. Okay, so remember, that could just be a scalar. That could just be a one-dimensional distribution. And then a product of the conditional probabilities of my detail coefficients at a particular scale, given the low resolution image at that particular scale. Okay. So if we have a model like this, how does generation work? How do we generate how do we actually sample an image to make this a bit more concrete? We draw a sample from our low resolution distribution I0 that gets us some tiny little image. We use that to generate a set of detail coefficients. And now we run those two things together through the inverse wavelet transform. And now we just repeat the process, but now using the next conditional distribution of detail coefficients. And again, through the wavelet transform to get us back to our high resolution image. Okay. And if we want to use this, for instance, to represent, if we look at this model, what we can see is this whole thing here, this is our model of an n by n image, an n squared image. Okay. But if I just ignore the left part of this model, okay, and I focus on this piece here, this is another normalizing, another wavelet model of an n/2 sized image, okay? And again, we can do the same trick, and now we have another, all built in as part of this, a model of an n/4 sized image, okay? So built in here, we automatically have models of all lower resolution images, at least by factors of 2, okay? We can also do super resolution with this model, just as a nice byproduct, because instead of going through all this stuff on the right, we can always just plug in an image at a particular resolution and start generating detail coefficients at higher and higher levels of detail, and apply the inverse wavelet transform as we go to get higher and higher resolution images out, right? One of the key advantages of this, though, I mentioned training time earlier, is if we look at what happens when we do maximum likelihood training with this, okay, we have the probability of our log probability of a high resolution image. We write that as all these probability, all these different probability distributions that we've constructed, the probability of the low res image, the probability, the conditional probability of all the detail coefficients given their corresponding low res image. this is just a sum of all of these different terms. And what that means is that all of these different models, all the models effectively of each scale can be trained completely independently of one another. Okay, they can be trained in parallel. They have no direct connections to one another through the training objective. Okay. All right. And what that does is it allows us to significantly decrease training time. So this is the training time of the GLOW model in total GPU hours compared to ours. Part of this is because of the scale structure. Each one of those individual models can be much, much simpler than an entire GLOW model might be. Part of it is that we can do much more efficient parallelization because all of those different scales can be trained completely independently of one another. Okay. We can do some quantitative evaluation. What we find is basically our performance is about on par with GLOW. So we're not really losing anything, at least quantitatively. I mentioned super resolution. That's kind of a nice application that we didn't really aim for when we set out on this project. But that was a low res image. Here's our upsampled version of it. Okay. And we can kind of zoom in on a couple of patches to see the detail that's getting added. We're still losing a little bit of fine detail at high resolutions, but it works reasonably well. Okay. So I'm going to stop here and just say thank you all for your attention before I run even more over time. It was my pleasure to be here. I'm very happy for the invitation, and I'm happy to stick around and answer any questions that people might have. Thanks.
Awesome. Thank you, Marcus.
Do you understand normalizing flows better, Matt?
Better. Still not. I'm still confused about them though.
Okay, I'll take better.
Do we have, maybe we have time for a couple of questions if there are any remaining?
Can I ask a question? Yeah, if my question is that if I0 is just a scalar, does it have a high enough generalization? Because normally the GLOW is just using a noise map, right? But now it's just use a scalar.
So the low resolution image in a wavelet flow doesn't have to go all the way down to kind of a single pixel image. You could take it to, you could stop at whatever is kind of a convenient low res image that you feel comfortable modeling as your lowest resolution. Arguably, you should have better generalization for that distribution than you should for a higher res one, because theoretically fitting distributions generally is really, really hard. But it's a little bit easier to do it in 1D than it is to do it in higher dimensions. So arguably that's a benefit at that point. One of the other things, by the way, with Wavelet Flow that I just want to mention here is I actually think Wavelet Flow will be most valuable if we were looking at 3D data. You could apply this to any high resolution signal that you wanted to learn a generative model of. So if you were looking at trying to model, CT scans or things like that, I think it'd be really kind of an interesting application, although I've not had a chance to do it. Okay. Other questions?
Hi, I have a question about, so you're talking about generative modeling of distributions.
Mm-hmm.
Do you have any, is there any work on conditional distributions? Let's say you have some site information, like a label or something. So you want to be able to slice up your distribution into different conditional distributions in order to...
Yeah, so you can use normalizing flows for conditional distributions. It's actually very straightforward. All you need to do is make those invertible transformations conditional on whatever extra information you have, and now you've constructed a conditional distribution, right? So actually both in Wavelet Flow and Noise Flow, both of those projects in essence use normalizing flows as conditional distributions. In Noise Flow, we were conditioned on the ISO setting of the camera, we were conditioned on the camera identifier, we were conditioned on the intensity, the clean intensity of the image. In Wavelet Flow, we have all these conditional distributions, which are, the conditional distribution of the detail coefficients given the low resolution image at that scale. I didn't really talk about that, but we actually just use a standard GLOW architecture, which takes as input the clean image as an additional component that kind of changes the behavior of the transformations themselves, right? So you can kind of think of conditional normalizing flows as basically just needing to construct conditional invertible transformations, which means you can just kind of stick in extra inputs into those functions.
That makes sense. Yeah. Thanks for the excellent talk.
Yeah, very welcome. Any other comments or questions? Yeah, so I'll reiterate what I said at the top. If you are curious to know more, you have other questions, feel free to drop me an email. I will reply when I can, given the time constraints of term, but always happy to chat.
Great. If anyone has questions, please feel free to unmute yourself and ask Marcus.
Okay.
If not, then Marcus is here for another hour. He is happy to meet for one-on-one meetings. And I think, Marcus, do you have an email ID to share here?
Sure, I can, let me,
Yeah.
I should have put that on my slides in retrospect, but you know, you can find me online pretty easily.
Sure.
My email address is up there, but that's I just put it in chat. There is my email address. So feel free to drop me a line.
Awesome. That would be great. So thank you, Marcus, for the wonderful talk and for engaging question answer session. It was really wonderful to have you here.
Thanks. Happy I could come. Quick point of logistics for follow-up meetings with students. Do I just stay on the same Zoom link, or do I need to go somewhere else? Do you know?
So that's up to you. I can keep this Zoom link on, and you can meet here. I can stop recording this thing, and you can continue here.
Sure.
Or if you prefer to go to Google Meets or something, I can do that as well.
This is fine. Yeah, I can stay here for convenience.
Okay, so I'll stop recording now, and you guys can chat casually, right?
Okay, great.
Okay.